Hello, everybody. Uh, for this recording, we're going to talk about DevOps and architectures that support DevOps. DevOps is a really interesting idea, and it's kind of a requirement if you're going to operate at the web scale architectures that we talked about in the last concepts video. And so in this video, we're going to talk some more about it and some of the architectures involved. So what is DevOps? Well, DevOps is a way to make it possible for our operations people to maintain the architectures that web scale applications require. By that I mean that traditional operations people came from a background where configurations were not code. You configured servers by hand, you deployed them in onesies and twosies, and that's how it worked. But that just won't work in a large-scale distributed architecture that is what we need to support these big web-scale applications. So how do you do that? Well, what you needed was some programming skills. And traditional operations people just didn't have those kind of skills. Even if they knew something about programming, they just weren't as good as development colleagues who program all the time. So DevOps says, well, let's take some of the skills of our developers, our development colleagues, and let's use them toward making the operations architectures better. And so that's kind of where we come from in all this. So how do we get to these large scale web applications? Well, everyone should know a little bit about development, and everyone should know a little bit about operations. Our development colleagues need to take responsibility for the changes that they've made when those changes are deployed into production and fail. Why? Because they're the ones who made the changes. They know how to fix the things that don't work. Operations folks may know something about them, but they're not going to be as good at it. And now coming out of this is this whole idea that if something's really hard, you should do it often so that you get better at it. Another way to say that is that it's safer to make many small changes than a small number of big changes. And from that, I mean that if you're gonna upgrade your application, do it often, but make each one of those upgrades really small so that if it doesn't work, and that happens, then to either roll backward to your old configuration or to roll forward into your old configuration is a lot easier if the changes that you make are really small. And we're talking teeny tiny here on a lot of web scale applications. They may add a small new feature, but they'll put a feature flag in front of it so that they deploy that code with the changes, but they have the changes turned off so that another change can be, let's turn them on, but only for a limited number of people that we trust, and so we can see if the changes actually work. So it's a really counterintuitive idea, but it works really well. It's safer to make many small changes than a small number of big changes. So DevOps ideas, well, things like release engineering, getting good at doing new releases, new upgrades, building the technology and taking the time to build the technology that is devoted only to upgrading and implementing new versions of your software. That's the whole idea behind release engineering, where we take the time to make the architecture, to make the tools available, to make it so that we can do these large number of small changes so that we can do them all day long without worrying about the change process itself creating a problem. We need to get that change process so that it works reliably enough so that we, if the changes that we make in the software cause problems, well, that's one thing. But if it's the changes in the technology that we use to change the software, if that causes problems, that's a whole different story. Orchestration is this whole idea of when we deploy new software, sometimes we need to have one piece of that software come up first and then be stable before we bring up another version. You guys probably all saw this in 221, where once you get that domain controller up and running, you have to have it running and stable before you have any clients come up. If you have the client come up first or just come up before the domain controller is stable, then the client is going to reach out for a domain controller and not find one and then stop trying. Well, that's no good. So orchestration matters, and finding the right order of technology to come up is an important thing to do. Continuous delivery. Continuous delivery is this idea of pushing new versions of software out as quickly as possible from our developers. Once they've completed it, tested it, we want to get it into production as quickly as possible. Why? Because the amount of time that our developers spend on developing new components, new features for our applications is a big investment on the company's part. And so the best way to make an investment useful is to get it into use. You know, if you're buying new trucks because you have a trucking company, you don't buy those trucks and then park them in the parking lot for 3 months. You buy them and you try and take delivery on them the day that you want to have them into production. Well, that's what we want with our software also. When our developers develop new components, new features, we want to get that out to our users so that we can start getting paid back on the investment we made in the work of those developers. Continuous integration is usually something we usually say it along with continuous delivery, and it's this idea of taking changes and get them integrated into our existing applications as quickly as possible. And so continuous integration is all about that process. Then this last one, projects that don't start at zero. What I mean by this is that instead of trying to develop everything and you know from nothing make a new application, that's not how you do it. If you were to come up with an e-commerce application, you would probably start out, at least originally, letting Amazon do your clearing of transactions. You might even have Amazon do the fulfillment of transactions, along with using Amazon's payment tools. Now, at a later date, you may decide, you know what, hey, we're spending too much on having Amazon do that, so we'll build our own. But you don't do that in the beginning. In the beginning, you rely on standardized tools to make up the parts of your application that aren't really that important to you, in that they're not the main basis of the application. The main basis of the application may be, I don't know, a dog toy store, in which case you want to concentrate on having the right dog toys, having the right website, having the right uh, those kind of basic things, but allow Amazon to do the payment side of your dog toy business, do the fulfillment side so that you have all your dog toys at Amazon's warehouse, and Amazon, you know, receives the orders and package up the stuff and sends it out to the users. Um, but then later on, you may decide, well, you know what, another really neat thing about our dog toy application is that we can fulfill orders much more rapidly than Amazon, or you know, whatever it is that you want to do. In which case you would then add that new component at a later date. Start with something that sort of works. And in this case, it's usually called a minimum viable product. and then add more components as you go. Iterate on that application. So start with something and then make it progressively better over time. That's a really important idea that comes out of this whole DevOps world, and it's very popular with lots of companies. Configuration is code. This is the subject of this class, in large part. Um, but it's hard to overstate how important this is. And we have the only kind of architecture that can support large scale, web scale applications is a distributed architecture. And this distributed architecture, we need to make it so that the machines that make up that architecture are not treated as one-offs. If you've worked someplace that has a small architecture, you'll get used to people saying, "Oh, this server usually works, but yeah, sometimes it's got problems. So we just reboot it a little bit more often than the others, and it's all good." Well, what that is just goofy saying, treat servers like cows, not pets. That's it. The way we treat pets is that we get to know each individual pet's, what they like and how they operate and all that kind of stuff. And that's fine for pets, but it's not fine for servers. We don't want servers that have little idiosyncrasies. We want our servers to function correctly all the time, or at least as much of the time as we can expect. In that, those servers are more like cows. When you have cows around, they're not pets. You don't get to know each individual one very well, except from their RFID tags. But cows do their thing. They come, they live their life, they do their thing, and then they go away to whatever their destiny is. And so if we treat servers like that, if we say, this is a server, this has a standard configuration, this will do its job in a standard way, when it stops performing that function in its standard way, it's gone. Now, that may be from a hardware perspective, or it may just be from a software perspective, where if a configuration no longer satisfies the requirement of the application, we can dump the configuration, but not the hardware, and reinstantiate the service on either some other piece of hardware or the same one. That's the same sort of idea. So treating our servers like cows means that we have them around, they do their thing. When we're done with them, poof, they go away. Not like pets. We don't rebuild servers. We don't um, reinstall applications into the same server. Most of the time, what we'll do is we'll have a service deployed on a server, and then if there's a new version of that service comes out that we want to deploy, we'll deploy it on another instance, and then we'll go to our load balancers and we'll take down this old instance and transfer the traffic to the new instance. And this old instance is just software, and it goes poof and it's gone. And the new instance now takes over the load and becomes the old instance again. So that's how we treat our servers. We don't get to know them well. We treat them like cows, do their thing, and then poof, they're gone. So, but this configuration as code has a really important side effect to it. That's if our configuration is going to be code, it should be treated like any other code, with versioning and testing and all that kind of stuff that our development colleagues have been doing for decades. We need to do that too. And that's another component of this class, is to think about the way that we treat software. Version control, testing, all of these things should be part of what we do. Systems architectures to support this. It's not going to be big monolithic servers where we have an entire application on one server. Why? Because it's really hard to manage a single server application. If the server bogs down, if it gets slow, how do we know what part of the application is causing the server to slow down? Sometimes you can tell, but a lot of times you're just guessing. So what's another way to do this? You take your big application, the monolithic application, and you break it down into lots of smaller components that are connected via well-known APIs. So if I take my big application, turn it into a number of small applications, then if this is my application that myself and my team maintain and are responsible for, that means we've got an API that connects into that, and we say, this is what we expect to come into our application. If there's something else that comes in to our application, it doesn't belong there, and we can't support that. Now, on the other hand, what comes out of our small application, we have an API there also, and it connects into other services that have expectations about what's coming from our application. And so as long as we maintain that outgoing API and deliver data into the next component in the correct fashion, and as long as we get data coming into our API that is what we expect, well, you know what? The rest of the organization doesn't really need to worry about how we fulfill the requirements of our small application. As long as we process the data that comes our way, send the right data out onto the next component, what we do within our little architecture, our little component, is up to us. That's really good for lots of different reasons. From a management perspective, we know what our application should be able to do. If it isn't performing properly, we can much more easily troubleshoot it. But more importantly, it also makes these big applications more manageable, because when you have take the big application, break it up into a whole bunch of smaller applications, those smaller applications can be managed by small groups of individual people. And what that means is that if you can work with a small group, then that small group can get to know each other, can get to know each other's strengths and weaknesses, and find ways to do the best they can on their single microservice that they're providing. In Google, how big should these teams be? Well, Google uses this idea of having two pizza teams. So the idea behind that is that each team that manages an individual component in a microservice architecture should be small enough so that you can feed the entire team on two pizzas. So depending on how hungry the individuals are, you're looking at anywhere from 6 to 10 people would be in each one of these teams. Well, if you work in a small group like that, you really get to know each other, and you can make decisions, and you can, make things better more quickly without spending lots of time getting approvals from everybody upstream as well as downstream from you in the overall application. So microservice architectures are the way these big applications are organized. And we'll talk more about it as we go. Then the last part is this mutable versus immutable architectures. So a mutable architecture is an old style architecture where if you had a web server and it's serving content out to users, and you either have a new version of the web files that you want to deploy, or you need to upgrade the software that's running on that web server, you leave that web server in place and then make changes to it. Well, that's fine except that if you can make changes to it, maybe bad guys can too. Wouldn't it be better if we said, here's our web server, and it's just a piece of software. So, I can't point at it. That thing, I can't do that. It's just a piece of software. In that piece of software is everything that our web server needs to do its job. And we deploy that into production on some, Docker environment or as a virtual machine or whatever. And then but we make it so that no one, not even us, can make changes to that. It exists, it's immutable, it's not changeable. If when the time comes, because it will, when we need to change it, what do? We start all over again. We stick another piece of software out there with our changed architecture in it. Once again, we go out to our load balancer and we disconnect the old architecture and we push our traffic to the new architecture. That old architecture, gone. We just delete it and it goes away. That's immutable. The neat thing about it is that if we can't change it, nobody can change it. That's the thinking behind it. And that's really important. So we have lots of different systems architecture ideas that support DevOps. I can't go through all of them, but service-oriented architectures, microservice architectures, we talked about that. High availability is a way to think about how we organize our architectures. That's our goal. But a better way to think about this is, say, resilient architectures, so that we know our architectures are going to get beat up and bad things are going to happen, but we don't care they if they take a hit. What we want it to do is to bounce back up, be ready to go. If we lose part of our architecture in a cloud data center in Seattle, if it fails, as long as we've got our another part of that same architecture in New York, and we've got a load balancer that can just say, oh, the Seattle architecture is down, let's push all our traffic to New York. That's resilient compared to making an application that will never fail. We know that's never going to happen. But resilience, we can do that. Load balancing is a key idea in all this stuff. We need to be able to push our traffic around to the parts of our architecture that are functioning properly and can accept the incoming workload. Service discovery, this is a problem too. If you have your services moving around so quickly, it was in Seattle before, now it's in New York. How do you make it so that the parts of your application that need to find these services can actually find them? That's a difficult thing to do. The networking, our old style networking, it's going to have a rough time with this highly changeable, highly resilient architecture. Everything that we've talked about so far says that applications change, and we want to make those changes as quickly and reliably as we possibly can. But everything that our old style networks are about is that applications don't change, that our networks continue to function exactly the way they did before. That's a mismatch, and we need to find ways around that. And so, software-defined networking, that's one way. There's lots of different ways to do it, but old-style cast-in-stone networks are not the way to do it. We need to make our networks support our applications because that's what they're there for. Monitoring our systems is really important. If we've got all these different components and we want to monitor all these different components, that means that we're going to have lots of monitoring, lots of metrics to keep track of, and we can't keep track of all of them on all of these servers. So we've got to really think about, what do we need to monitor? What are the important metrics that we need to keep track of? Storage, is a huge deal here because we've got lots of storage, lots of servers, lots of components, lots of files to keep track of, and it's really hard. Containers are a good idea in this, whether they're Docker or I forgot some of the other ones, but the other various kinds of containers that are out there are really good. But containers require container management. Containers can move around so quickly we can just lose them. So we need something like Kubernetes to keep track of our containers and manage them in the face of this rapidly changing architecture.